Okay, we're rolling. This session is being recorded and it'll be put later on the recorded presentations page in the left column of my TCC Blackboard. And on the schedule for today, we're covering modules 11 through 13. And we're going to cover the traditional IPv4 addressing and subnetting. Then we'll look at IPv6, the replacement protocol. That's about 20 years old now. And then a few frames on Internet Control Message Protocol, which is the reasoning behind the echo request and echo reply, echo request and echo reply, the ping command that we use a lot in network troubleshooting. Okay, we're rolling. The audio is going, and so I'm going to stop sharing this, and I'm going to start sharing. If I can find it here. Oh yes, I'm going to start sharing my application screen. I think it's this one. And then let me bring it to the forefront here. Oh, good. We have frames. Okay, good. So what we're talking about in this particular part is when I use the word legacy, you'll think about obsolete, something that shouldn't be used anymore. IPv4 was the original internet addressing scheme. But the problem is in the mid-90s, it started running out of addresses. So we started transitioning to IPv6. So as a general rule, as a good technical and business practice in the future, we should try to move everything to IPv6 and get rid of our IPv4 stuff. But it's still around and we're still using it quite a bit. So with IPv4 addressing, which is way back from it's from the late 70s, early 1980s is when this addressing scheme came out. And there were, these guys that designed this were quite clever because previously every addressing scheme had a fixed size network. And so they came up with the idea of, why can't we have large networks for big companies and medium-sized network for medium-sized companies and small-sized networks for small companies or small branch offices. So they came up with this idea of class A, B, and C networking. And each class was a specifically assigned network. So class A, for example, millions and millions of possible addresses, down to class C, which is what your ISP gives you to use, what your home router gives you to use at home. And it's 200 odd addresses. That's plenty for a home user or a small business user. So in order to figure this out, electronic devices, the binary devices like routers and switches and host workstations, would look at that first octet of the address and look at that first bit. So if you look at the binary equivalent of all the numbers between decimal 0 and 127, well, the 8th bit is the 128 bit. So if they're less than 128, that 128 bit would always be set to 0. So all those numbers from 0 to 127 were called a class A address. All the numbers that had anywhere from 128 to 191, the first 128 bit was set because it's 128 or more. And if the second bit, the 64 bit, is not set, that means you can only go from 128 to 191. And then the class C network, the 128 and the 64 bit were set. That adds up to 192. Sound familiar? 192.168. So that range of addresses went from 192 to 223. And there was a couple of extra classes at the end, D and E. For D is used for multicasting, and E is used for experimental rocket surgery stuff. So these divisions are at the octet boundaries. For example, 192.168.1.1 is a class C address, and we express it as the period between the 3rd and the 4th octet is the boundary between the network portion of the address and the host portion of the address. In the early 1990s, they added the ability to subnet a network into smaller networks. So a large corporation that would be given a class A network could subnet into smaller networks for its various branch offices. So when we subdivide a network or subnet a network, we're going to take and we're going to sort of borrow binary robbing of Peter to pay Paul. We're going to borrow binary bits and create some new subnetworks that are smaller than my original network. There was a default subnet mask for each network. So for example, our 192.168.1.1 type address we use in all labs has a default subnet mask of 255.255.255.0. Every class A, B, and C was assigned a default subnet mask. So every IP address, every IP network has 3 types of addresses. In the network address, all the host bits are set to 0. If it's a broadcast address, all the host bits are set to 1. And if it's in between those, if it's not totally 0 or all 1s, the host bits will vary, and those are the valid host addresses we can assign to routers and switch management addresses and servers and printers and workstation employee and student desktop PCs and so forth. So for a host machine to communicate with another host machine on the same network, which means they're plugged in at the same switch, they can hear each other's broadcasts. They have to have the same network portion or network prefix. So this means that every time we have an IP address range, we're automatically going to lose 2 network addresses that we can't allocate to devices. When all the network bits are 0, we're going to call that the network address, sometimes called the wire address or subnetwork address. And when all the host bits are 1, that's reserved for the broadcast function. Remember, our big 2 things that we use for broadcast are the ARP request and ARP replies and the DHCP function. So the number of hosts that you can have on a network, you're always going to have -2 minus that number. So taking a Class C network, see, does my mouse wiggle up here? Oh, good, it wiggles here. Okay, let's take a Class C network, which we're more familiar with, kind of like the 192.168. So in the Class C network, or /24 subnet mask, 255.255.255.0, we have 8 host bits remaining. So what is 2 to the power 8? Well, 256, but we lose 2 of those because the all zeros value, the 8 zeros value, is reserved as a network identity value. And the all ones value is reserved for the broadcast function. So if we take this formula 2 to the power 8 and then subtract 2 from that, well, 2 to the power 8 is 256 minus 2. We have 254 valid network addresses, host addresses, device addresses that we can assign to the various devices we have in our network. This worked fine until about 1995, and all the networking equipment just counted the number of, looked at the first digit and figured out it's a Class A, B, or C address. But when we started running out of IP addresses, they came up with a scheme called the variable length subnet masking, which means that we can give you any number of network bits and any number of host bits, and this is less wasteful. So we're going to look at classless addressing a little bit later, but first let's look at classful addressing. Let's look at our calculating of address. We want to take our legacy IPv4 network and find out for any particular host address, let's say your host is 192.168.1.10. That's the number of the PCA value. What network is that PC on? What broadcast address is on that network? And what other host addresses are available on that network? And then how can we divide that network into smaller networks? Also, here's our humorous Homer slide. I like to compare network numbers in IP networking with area codes in the telephone system or zip codes in the mail system. So the network prefix defines a bunch of devices that are in one particular room or building for a company. All the host machines in that network can communicate with the other devices on the same network. Physically, they have to be plugged into an Ethernet switch or a hub. But all devices logically have to be configured with the same network prefix number and the same subnet mask so that they know what the values of all the others are and what to expect. So here we have in this diagram, we have 4 networks that are connected to a router. They're not showing us the switches, but there's a network, there's an Ethernet switch or hub on each one of those 4 segments that connects all those PCs together, and then that switch plugs into a router port like we'll do in the lab for this week. So routers use this network prefix to build their routing tables. Host machines cannot be given a network address, they're only a host machine. The network address is the address of the entire wire for that all those 4 machines that are on that one particular network. When we have an IP address and the network number is all zeros, that's the reserved network identity, the network number for that network. So for our network that we always use, 192.168.1. something, the address 192.168.1.0 is the reserved network identity for that entire network that has a little over 250 available slots. The 192.168.1.255 is the broadcast. That's a reserved special function broadcast address for that particular IP network. So if a host needs to send a broadcast, he'll use that same network prefix, and then he'll set all the host bits to 1. So we cannot assign that broadcast network to a host machine. It's reserved for the broadcast function. The Ethernet switch or hub is going to receive it, and he's going to flood that to all of the other ports so everybody can hear the broadcast. So if it's an ARP request or a DHCP request, it needs to be flooded to all the other machines, and the one machine that can help them reply to the ARP or grant them an DHCP address, they'll respond to that request. So the host number is the portion of the IP address that uniquely identifies the individual host. Each one of the machines in these 4-segment networks we see in the graphic has got a range of addresses that's given out to that particular network. Now the subnet mask is the, I don't like the word mask. It sounds like it's the Phantom of the Opera and it's trying to hide something from you. I would rather call it the network yardstick or the network ruler, because the subnet mask tells us, the ones in the subnet mask tell us where there are ones, are the network bits. Where there are zeros, these are the host bits. So we can look at the subnet mask and determine how big our network is, how many host bits do we have. The default or natural subnet mask is based upon the default number of bits. So for a Class A network, for example, we normally have 255.0.0.0, which means there's 24 host bits. 2 to the power 24 is a pretty big number. For a Class B network, it's half and half. We have 255.255, which in binary is 16 ones. That's the network prefix. And the 0.0 at the end represents our 16 available host bits. That's 65,000 possible addresses. And then our more normal size small networks that we use typically in Cisco Academy labs, we're going to use like a Class C network, where there's 24 network bits, 192.168.1, for example, very familiarly. And then we have 8 host bits. So that gives us over 250 usable, available addresses that we can assign to devices and still have, the all zeros network value and the all ones broadcast value. You can't use those. So in Class C networks, their range is 192 to 223. There's 24 network bits, 2 million networks, and so there's 8 host bits remaining. It's up here. Okay. So the number of hosts per network is 2 to the power 8, 256 hosts. However, we lose 2 of those. We lose the all zeros value for the network identity. We lose the all ones for the broadcast. So we get 254. And the default subnet mask is 255.255.255.0. So the Class C subnet mask tells us the first 24 bits are network prefix numbers, network identity numbers, and the last 8 bits are for the host numbers. So the very first host address, here we have written in binary, network address, and the last 8 bits are all zeros. Doesn't matter what the first 3 octets are. It could be any network that we could gin up from those possible numbers. The host bits, when all the host bits are 0, here our subnet mask is /24. That's reserved for the network identity. The last address is reserved for the broadcast function. So when the 255 in the host address, that's all ones in binary. So that's a reserved address that we don't give to a host, but rather we reserve that if a host machine wants to send out a broadcast message on that network, he'll use that .255 address. The host portion is all zeros, and the network portion is all ones, so we lose 2 for that, and the number of usable host addresses we get on this network then is 2 to the power 8, which is 256, minus 2, which is 254. So we get everything from binary 1 to binary 254, and those blue and yellow frames that are at the end of the slide. So 250 full addresses, which is 256 minus 2. Now a Class B network, there's 16 network bits and 16 host bits. So the number of networks is a bigger number. The number of host bits is 16. Well, 2 to the power 16 is 65,536. But we lose the 16 zeros for the network identity. We lose the 16 binary ones for the broadcast value. So the number of usable hosts we get on the network is the 65,536 minus 2. And the default subnet mask here is a /16 or 255.255.0.0. So that very first address is the very first address in this range of this arbitrary network he came up with in the slide, 146.84 in red. Our host bits are in blue. So when the host bits are all 0, this is 16 binary ones. This is a reserved value. We can assign this to a printer or a router or a computer. This is reserved for the router to use in his routing table, because routers use their routing tables to figure out what networks they can communicate with. Just the networks, not the individual hosts. Switches have MAC address tables. They memorize individual hosts, but routers don't. So the first address is reserved, and the very last address, all binary, 16 binary ones, that's a reserved broadcast address on this particular network in red. We get all the ones in the middle. We get the 65,534 possible addresses in the middle that we can have for our network if we need that many, if we would use this network range, if we needed that many addresses in a network. Now, Class A networks are the largest. There's only 8 network bits and 24 remaining host bits. So 2 to the power 24 gives us over 16 million possible host addresses, but we lose 2 of those. Instead of the 216, we only get 214. There are some Class A network addresses that are not usable. It's supposed to go from 0 to 127, because when you set the host, the 8th bit, the 128 bit to 0, you get everything from 0 to 127. But there's a few that aren't usable here. He lists a couple here. The 0 network is reserved for our default routes, which we'll get to in a later course. 127 is reserved for the loopback test. When you see ping 127.0.0.1 on your desktop PC to see if your TCP/IP code is okay. So we can't use that. And there's a couple of others that are reserved. The 10 dot private address. I think the Pentagon stole a couple of them. So there's fewer than 128. So on a Class A network, the first 8 bits of the network numbers in red, the last 24 bits of the host numbers. If I set all 24 of those binary bits to 0, that's a reserved value for this particular network. The 66 network, 66.0.0.0 is the reserved address for the network itself. The broadcast address for this network is going to be 66.all1s, 255.255.255. That's reserved for the broadcast function. We cannot assign that to routers or switches or servers or printers or desktop employee or student machines or anything that needs an IP address. We can't use those addresses. Those are reserved respectively for the network identity and the broadcast function. But we get all the ones that are in the middle from 0.0.1 to 255.255.254. We can give those addresses. So for Class A network, that's millions and millions of addresses. So let's take a look at this particular IP address, 130.61.22.204. What class network is this? Well, it's more than 128, so it's a Class B. It's less than 192, so it's not a Class C. What is a default subnet mask? Well, they gave you the /16. That's equivalent to 255.255.0.0. The network address is going to be, let's set all the host bits to 0. Well, 131.61.0.0. So on this particular host machine, 130.61.22.204, his network address, he figures this out himself, is 130.61.0.0. The broadcast address is, instead of the 2 zeros in the 3rd and 4th octet, let's make them all binary ones. So if this workstation needs to send out an ARP request, he would send it out to 130.61.255.255. How many usable host addresses are there on this network? Well, 16 host bits. 2 to the power 16 minus 2 for the all zeros and all ones. We get over 65,000 possible addresses on this particular network. So they range from 130.61.0.1 all the way to 130.61.255.254. Now let's look at another address. Now he kind of gives it away here, tells us /24. The 197, well, that's bigger. That's 192 or bigger, so it's a Class C. The normal default subnet mask is a /24 or a 255.255.255.0. Most common subnet mask we usually see in most networks, because most networks we keep them down below 200 users or so there's not so much broadcast problem. The network address is the network prefix 197.101.28.0. The network prefix is the first 3 octets. The 4th octet is all zeros. That's the definition of a network address, is all the host bits are zeros. The definition of a broadcast address is all the host bits are set to 1. So that 4th octet, instead of being all zeros, it's 8 binary ones, which is in decimal is 255. So the number of usable host addresses on this reasonably small size network you would use in a home or small business is the number of host bits, 8. 2 to the power 8 is 256, minus 2 is 254 available addresses. So they range from .1 to .254. I have over 250 addresses I can assign to all my devices in my particular network. And now it looks like a sort of a Class A address. It's between 1 and 126, so we know it's a Class A. The address class is A. Subnet mask is, well, /8 is 8 binary ones and then 24 binary zeros, or 255.0.0.0. The network prefix is the network number, which is 64, and the 3 remaining octets, the host bits, are now zeros. Definition of the network address is all the host bits are 0. And the broadcast address, all the host bits are set to binary ones, or 255.255.255. So we get quite a few usable host addresses on this network. Probably would be impractical to put them all in one building. You'd get too many broadcast dorms and stuff. We're probably going to subnet this network up into smaller pieces. So it ranges from 64.0.0.1 through 64.255.255.254. Now let's look at some basic subnetting. The IP addresses haven't started having a problem with this in the mid-90s, and they started running out of available IP addresses. If everybody used an entire class A, B, or C network, they would waste too many addresses. So if I was an organization with 256 hosts, I could not be issued a Class C address because they only get 254 hosts with that. Remember the reserved host, reserved network value and the reserved broadcast value? So these organizations, even if they only needed a few hundred or a few thousand addresses, they were given a Class B address. This happened to me when I was at Harcourt in the 90s. We had only about 10 or 12,000 employees, but we were much too big for a Class C network. They just gave us a Class B network, 167.208. I can't remember. I'll never forget it because I statically configured it like 10,000 times. But we wasted 80% of our address space. We only need 10,000 addresses. We didn't need 65,000. 55,000 addresses we wasted, but it was our address. So we want to take our own addresses and subnet them up into smaller pieces. We're going to do traditional subnetting first. Then we're going to look at a method called Classless inter-domain routing, or VLSM. In our late fall class, when we do routing protocols like OSPF, we're going to look at network address translation, which is what all the home routers do. So if I had a range of network addresses that I wanted to divide up amongst various branch offices, I can take that range of addresses that was given to me and divide it up into smaller areas. Much the same in which the telephone company in Fort Worth, which owns the 817 area code, divides up their 817 area code in lots of branch telephone offices for the 10,000 customers or so that are in that particular region. We're going to break it into smaller, more manageable units. This company has 4 networks connected by a router, and the network numbers have to be unique, just like the area code number has to be unique. 817 for Fort Worth, Tarrant County, 214 for Dallas County. In this particular case, the company's been allocated a Class B address of 131.15, which is a pretty large network with over 65,000 possible networks, and he's going to use those for all of these networks. So what we're going to do is we're going to take that 131.15 and we're going to divide it into, we're going to rob the binary robbing of Peter to pay Paul. We're going to steal some of those host bits and give them back to the network prefix and create an extended subnetwork mask and create some new smaller networks. Now, this is not the Federal Reserve. We can't make money out of nothing and add $10 trillion to the economy just by running our printing presses. We only have a fixed number of binary bits. In the case of IPv4, we only have 32 bits. There's nothing we can do to gen up magical numbers here. But what we can do is take the 16 bits that have allocated to us, and we can subdivide that up into our branch offices. So in this case, they took their 131.15 network and made the .1 network and the .2 network and the .3 network and the .4 network. And don't forget, if you use a least link to link your locations together, that's another network. That's going to be .5. So network numbers have to be unique, and this is where some planning helps, so we can plan for future growth and expansion and try to make efficient use of the addresses that's been given to us. So we're going to subnet a network, and what we're going to do is we're going to do this binary routing of Peter to pay Paul. We cannot go back and create a new network prefix because those are given by the ISPs and the name and number 30 people. I can't use someone else's number. They'll cut me off. But what I can do is use my 16 bits, my host bits. I can borrow those bits and create new networks. In this case, the company has borrowed 8 bits and created a new subnetwork that's a /24 instead of a /16. Since he borrowed 8 bits, how many new networks can he create now? Well, 2 to the power 8. He can create 256 new networks and allocate them to all his various branch offices throughout the world. And then each office will have now 8 host bits. And if there's less than 250 devices in use at each office, that would work fine. This is what we did at Harcourt in the 1990s. We had 167.208. We borrowed 8 bits, and my office in Fort Worth allocated 167.208.209. And then I could use the last 8 bits for the devices in my particular office. So it's a subnetwork of the original, or a subnet. We borrow bits from the host portion and assign them to the network portion. We binary rob Peter to pay Paul. So the borrowed bits have now become the new extended subnetwork mask. It used to be 255.255.0.0. Now it's 255.255.255, and we have 8 host bits left in this particular network to use. Those are my remaining host bits that I'll use to assign to all those devices. So the original subnet mask, when we borrowed, now our new subnet mask is going to be 255.255.255.0 for this one network that we created and all the remaining other 255 networks I created when I borrowed 8 bits. I have to borrow in descending order, starting from the leftmost bit position and working to the right. I cannot go back and borrow bits going left. That's stealing someone else's values, and the ISP will not allow that to take place. You have to use at least a minimum of 2 bits. You have to leave at least a minimum of 2 bits for host addresses. Because if I only have 1 bit remaining, the only possible values are 0 and 1, and those are reserved values for network host identity and broadcast entity. So that /30 is the smallest I can borrow. That gives me 4 combinations of which 2 are usable, which is perfect for a point-to-point least data link between 2 offices. Okay, so if the remaining host bits of all zeros cannot be assigned as a host address, or all ones, because that's reserved for the network identity function and the broadcast function. So to determine the number of subnets or hosts, the number of subnets we're going to get, in this case, we borrowed 8 bits. So 2 to the power 8, we got 256 new smaller networks. The usable host for subnet was the same rule we've always been using so far. We now have 8 host bits remaining because we borrowed 8 and gave them back to the network. In this case, we have 256 new network subnets that we created, and each one has 8 remaining host bits, so they'll have 254 valid addresses because they have the all zeros reserved for the new individual subnetwork value and the broadcast for that network. Now, taking a default class C style network where we have 24 bits and 8 host bits, if I don't borrow any bits at all, that's just one network. I have 8 host bits, I get 254 usable hosts, it's a /24. What if I wanted to divide that network in half? Maybe I got 2 offices, 2 floors in an office building, 100 people in each one. So I need 2 smaller networks. I could borrow 1 host bit. Now I have 7 host bits remaining. That's 126 hosts on those networks. I could borrow 4 bits and create 4 networks with 62 hosts. I could borrow 3 bits and create 8 subnetworks with 30 available host addresses. And I can continue till this is the last one I told you about here. If I borrow 6 bits, it gives me 2 usable host addresses, which is okay for a point-to-point data link where you only need 2 addresses. But if I borrowed 7 bits, remember the rule, you have to leave at least 2, then only leaves 1. Oh, well, 2 to the power 1 minus 2 is 0 usable. So that's unusable. We cannot borrow 7 bits. We always have to leave at least 2 bits. So let's take our Class C network, and we're going to use the network 192.168.80, and we need 4 networks with 5 hosts on each one. And we want to leave some room for future growth and expansion. So let's see, I need 4 networks. If I borrow 2 bits, that would give me my 4 networks, but there's no room for future expansion. And it was 62 usable hosts, but I only needed 5 hosts. If I borrow 3 bits, well, 2 to the power 3, that's 8. That's 8 possible subnets. So I got 4 I can use now and 4 in the future for future growth and expansion. and 30, that's more in line with this. So if we gave us 3 bits, that would give us 8 subnets with 30 usable hosts on each network. And that way I've got enough for my current requirements and I have enough to grow with in the future. Okay, there's something called the magic number. The magic number is going to be the method that we can create our subnet charts without having to do any binary in our heads whatsoever. Just using decimal numbers. We're used to decimal numbers. So if we have 5 hosts, remember we borrowed 3 bits and we have 5 host bits remaining? So our magic number is the number of bits in the host field we have remaining, 2 to that power. That's our magic number. That's going to be our multiplier increment that we're going to use to create subnet masks, subnet charts. Okay, so let's take this network 192.168.80.0 and we're going to create 8 networks, and we're going to use the first 4, and the last 4 are going to be future growth and expansion. So our original network address is 192.168.80.0. Now, what's our magic number? Oh, it's 32. Okay, so I'm going to go ahead and put the broadcast for the entire network that we are borrowing from there. And let's create our first network address, our first sub-network address. We're going to take that magic number and we're going to number starting, this computer science professors always count starting from 0. So instead of saying 1 through 8, we say 0 through 7. And it makes sense here because if we take our magic number and we multiply it by 0, the last octet is 0. Well, our magic number is 32. So the network number 1, what's 1 times 32? It's 32. What's 2 times 32? 64. We're not doing any binary, are we? We're doing it in decimal numbers. Oh gosh, you've been doing this since the 3rd grade. You should be able to do this pretty easy. 3 times 32 is 96. 4 times 32 is 128. And we created our subnetwork values. Now, what is the range of addresses that we're going to get? Remember that we have 5 bits, and the 0 is reserved for the network identity, and the all ones are reserved for the broadcast. So if we take this number here of the next column and subtract 1 from it, that's going to be our broadcast address for the preceding network. So 32 minus 1 is 31. Okay. 64 minus 1 is 63. 96 minus 1 is 95. 128 minus 1 is 127. 160 minus 1 is 159, 192 is 191, and 224 is 223. Now we have our broadcast addresses, reserved broadcast addresses, and network addresses. What are our viable, what are our allowable range of addresses we get to assign to our host machines? The ones in the middle. 0 plus 1 is 1. 31 minus 1 is 30, so we get from 1 to 30. From the range here, 32, we get 33 to 62. We just get the numbers in the middle. So we've now created our subnet mask chart. Our subnetting chart for this particular network. And we didn't have to do any binary nonsense. Well, we had to know that 2 to the power 5 is 32. So we have 8 subnets with 30 usable hosts each. And then we can add more networks in the future, and we wouldn't have to change our IP addressing scheme. If you're doing this for a Class A or B network, it's the same. You're simply working with more bits. So when I was at Harcourt, we had that 167.208 Class B/16 type network prefix. We had 16 bits to borrow from. So in our case, we borrowed and created 250 usable networks, subnets, and we had 250 people at each site. And the sites that had more than 250 people, we just assigned them another subnet. So we're going to do this. We need to determine how many networks we need and the number of hosts. This has to be an achievable goal that we can do. If I told you to take a Class C network and come up with 12,000 employees addresses, well, you only have 256 possible values. That's impossible. You need a Class B address to do that. But we can simply we could take a Class C address and do that like we did, 4 offices, 5 people in each office. We have enough bits to do this. So determine the number of networks you need. That's going to determine the number of bits you're going to borrow. And then the number of bits left over, 2 to that power. We did 2 to the power 5, made 32, was our magic number in our example. And then we subnet to do this. So let's do one that's similar to what I did back in the 90s with a big publishing company. Let's say you're a worldwide organization with 7,500 users. You've got 10 worldwide central offices, and each of these 10 worldwide offices has their own branches. And their size ranges from 1,000 to 3,000 users. Well, fortunately, someone reserved a Class B address for the company back when they were easy to get in the early 90s, and that'll be sufficient. Each central office handles their own network, and all I got to do is hand out the 10 offices values to them. So we're going to use 172.25, and we're going to divide this up. Give enough addresses to Central 1 so he can have his branches, Central 2 so he can have his branches all the way to the 10 ones. Okay, so how many bits should I borrow? I need 10. If I borrowed 1 or 2 or 3 bits, that's not enough new networks. I need at least equal to or more than. Well, if I borrow 4 bits, that gives me 16 subnetworks. Well, I need 10. That's enough with some extra left over for future growth. And I have 12 host bits remaining, which is 4,094 usable host machines. Well, we have 3,000 people at the home office, so that's a workable value. If I borrowed 5 bits, I'd have more than enough networks, but wouldn't have enough host bits for the home office. So the 4 bits is a happy medium in this case. It makes it work out. You kind of got to two-edged sword here. We got to balance this: the needs of how many subnetworks versus how many host machines on each network. So let's do our magic number. In this case, it's the interesting octet, which is the last non-zero octet in the subnet mask. And 240 in decimal is 11110000 in binary. So we borrowed 4 bits, stole it from the original host portion, gave it back to the network sub prefix, and we've created our 16 new networks. And there's 4 host bits remaining, so our magic number, our multiplier, is going to be 16. Let's construct our subnet chart. So we started with 172.25 and we ended with 72.25.255.255. So our magic number is 16. Well, 1 times 16 is 16. 2 times 16 is 32. 3 times 16 is 48. 4 times 16 is 64, etc., etc. We might subtract 1 from all these values to come up with our broadcast values. And then we subtract 1 from this to have the ending value and add 1 to this to get the range of values for each of those individual subnets. And now we've created a subnet chart that we can use. We got 1 through 10 we can use, and then we have some spares for future growth and expansion. And there's plenty of host bits, 12 host bits on each one of these new subnetworks to be up to 4,000 odd host machines on each one of those networks, and we won't run out of addresses. Okay, well, let's see now. I need to stop this one. And then we need to start this one. Okay, hold on, I gotta reshare it. One of the problems with the original subnetting was we were, in certain circumstances, we were stuck with, we had to have the same subnet mask everywhere in the network. Variable length subnet masking is a method that if we are using the right kind of routing protocol, which we won't get until the later part of fall, it allows us to create a subnetting scheme where we can borrow, instead of having to cut the pizza exactly into 8 equal slices, which is what our traditional subnetting is, we can cut the pizza into a really big piece for dad and a smaller piece for mom and a little piece for baby. And we can create variable sizes on this range of addresses we've been given out. So we're going to create large subnets for our local area networks where we need lots of addresses for our employees, and we can use very small subnets for like the WAN links, so /30. So it's going to, oh, I'm working with the wrong one. Hold on. Local check, we're still okay. Good. So let's look at standard subnetting like we did before. We've got 2 Ethernet networks at the home office. Just wiggling, showing up. Okay. We got 2 Ethernet networks at the home office, and we got a Site B remote office and another branch office, Site C. And they've been given the network address. Oh, oops, hope that don't come out. How many network addresses? How many networks are there in this scenario? Wiggle up here. Okay, so let's count our LANs. We got 1, 2, 3, 4 LAN-based, probably Ethernet-based networks, and then we have 2 point-to-point links. So we have to lease those from internet service provider or from a telephone company or something to get those links up. So 1, 2, 3, 4. We got 6 networks. So I need 6 networks. Now, how many host machines are needed for the very largest LAN? Well, at the back of the home office, we have 2, maybe there are 2 floors in an office building, and there's 25 users on each one. So there's 25 users there. Oh, there's a secret gotcha here. The default gateway port on the router, that's going to be 26. So we need at least 26 host machines. How many bits do I need to borrow to address this particular network? So if I borrowed 3 bits, that would leave 5 bits remaining. And if I borrow 3 bits, well, 2 to the power 3 is 8. That gives me 8 usable networks. And each network will have, well, 5 bits left over. 2 to the power 5 is 32. Minus 2 gives us 30 usable addresses. So we'll take 4 of these networks for our Ethernet-based networks. That leaves us 4 networks left over. And then we'll use the remaining to use for our point-to-point links. We'll have a few left over for future growth and expansion. So let's do this standard the /27. So our magic number is going to be 32. We have network 0, 32. 32 times 2 is 64. And we get our network addresses, our subnetwork addresses. This is OK for the main site, where we really need all 5 bits. For the 2 branch offices, we're kind of wasted a bunch of addresses. And for those point-to-point links where we only need 2 addresses and we're using a whole network with 30 available addresses, we're wasting 28 addresses. Well, so this is a concept of, instead of a pizza in a box, it's a subnetting in a box. Here's our Class C network. Think of the graph paper you had in math class in high school. Let's create some lines in this. If we borrowed 1 bit, those 256 addresses would be 2 banks of 128 addresses. The subnet mask in this case would be 255.255.255.128 because I borrowed 1 bit, the 128 bit. You borrow from up to down. If I borrowed 2 bits, I would get 4 networks, each with 64 addresses, and our subnet mask would now be .192. If I borrowed 3 bits, which is the scenario we just talked about using, I've got 8 networks with 32 addresses in each one, and the subnet mask would be 255.255.255.224. And if I borrowed 4 bits, that would create 16 networks. With 16 host addresses, we only get 14 that we can use in each particular network. So here's the deal with variable length subnet masking. We haven't talked about routing protocols, hardly any. But some older routing protocols were classful routing protocols. They only send the network prefix to the other routers. Routers gossip with each other, tell each other about networks. So with the RIP version 1 and the IGRP, which is Cisco proprietary early protocol, they didn't share the subnet information. So for that reason, we had to use the same subnet mask everywhere in the entire network. Classless routing protocols do send both the network prefix and the subnet mask. So now that we have that additional information, we're free to use whatever subnet mask, any mixture of subnet masks we wish to use in our network. Now, all these protocols that are listed here, right now in the CCNA, there's only one that we're going to study, and that'll be in the last half of the fall, and that'll be OSPF, Open Shortest Path First. Oh dear, I didn't have my mic turned on. Okay, my mic is turned on now. Okay, good. So IP version 4, IP version 6 is addressed as 128 bits with hexadecimal. So to make those numbers not be quite so large, what I can do is omit leading zeros. So in this case, this address had lots of zeros. I can just drop the zeros. And that will make the number a little bit smaller, a little easier to read. Another rule is if there's a bunch of zeros in a row, in this case, we've got all these zeros in a row, any string of zeros can be replaced with a double colon character. You can only do it once. If you do it more than once, it becomes ambiguous. You can't tell how many are in each one. So in this case, these 12 zeros was replaced by double colon. We essentially took this part here, and we removed it, and we got the colon here, and the colon here was our double colon. So that's a compressed format. It's easier on the eyes to read, and it can't be misinterpreted because the colon can only be used, the double colon trick can only be used one time. Now remember back in IP version 4 legacy, we had Unicast, Multicast, and Broadcast. In IP version 6, they've changed the name of the broadcast function and they're calling it an Anycast. The two most common uses of broadcast in the IP version 4 world was ARP requests and ARP replies, and the DHCP broadcast to learn our whatever IP address we're supposed to use, because we don't want to, in most environments, we don't want to statically configure the IP addresses. We want to use a DHCP server or some mechanism where they can automatically get an IP address. So IP version 6 doesn't, they're not going to call it a broadcast address. It works like a broadcast. They're just not calling it a broadcast, I guess, so they can feel better about it being no broadcasts. So the IP version 6 multicasted, all nodes multicast, is the same exact effect as a broadcast address, except we're just not going to call it a broadcast anymore. So if you see a test question, are there any broadcast functions in IP version 6? The official answer is no. Now IPv6 prefix length, this is the network prefix in IP version 4, which could be 8 bits or 16 bits or 24 bits or any number if we borrow bits. Universally, in IP version 6 at the user level, it's going to be a 64-bit prefix. And it's going to be a 64-bit, instead of a host ID, now it's called an interface ID. So this is 64-bit division, exactly dividing the 128 bits into two 64-bit chunks, is used 99% of the time. There's a feature in IP version 6 called Stateless Auto Address Auto Configuration that is a replacement for DHCP, so you can come up with a valid, unique IP address to use on this particular network. IP addresses have two types of unicast addresses. A global unicast address, similar to a public IP version 4 address. They can be routed through routers. And the linked local address is kind of like, when you do a broadcast in IP version 4, the broadcast never crosses the next router. It's only of interest, locally significant interest only for people on that network. They're trying to do an ARP request or reply, or they're trying to get a DHCP server to get them an address. So all workstations will come up with a linked local address, and they're going to take the prefix that they get from the router, and they're simply going to generate up a 64-bit unique host address, or they'll take their MAC address and turn their 48-bit MAC address into a 64-bit interface address. The unique local addresses, similar to the RFC 1918, this is the 10, the 10.172.16, 192.168. The IP version 4 addresses were meant to isolate and provide some security. Now IP version 6 has better security built into it, so we don't have to use this. So globally unique addresses have the first 3 bits of 001. So right now, all the global IP addresses that are being allocated are going to start with 2000 or 3000. It's always going to be the first hex tet. But that's a small portion of the available addresses. We have plenty of room for future growth and expansion using this scheme. The global routing prefix is it would be assigned to us by our provider, such as an internet service provider. The subnet ID is the field. If we're a large company, we can take our subnet field and we can do what we just did with IP version 4 in the last chapter. We can create 16 subnets or 256 subnets or how many we use, and we're going to use the subnet ID for this. And then the last 64 bits remains the interface ID. The link local address is used only within that particular network. It's kind of like a broadcast. It can't leave the individual network. So every IP version 6 enabled network interface automatically he's gonna make up his own link local address. You can specify it if you want to, like FE80::1. But if you don't tell him one, he'll make up one of his own, because he needs that in order to find his friendly neighborhood router and figure out what his IP address should be and things of that nature. So if it's not configured manually, he'll create one automatically. And they're in the range FE80. FE80::1 is a common value you would put if you manually specified it. So the global unique address on the router, when we use commands before, we might say IP address or show IP route. On the Cisco routers and switches, now the new commands for IP version 6, you say IPv6 address or show IPv6 route. You just change the word IP to the word IPv6, and you can run dual stack and have them both run at the same time if you need to. So for example, on this lines of code, we go to our gigabit Ethernet port 000, and we specify the IP version 6 address. And it looks like a globally unique address. It starts with 2 or 3. As a matter of fact, this special address, 2001 DB8, is a reserved address for documentation and training. That's what we're doing here. We're doing training in Cisco Academy, IPA training, network training. Of course, we have to give the command no shutdown. Now, if you're running a dual stack environment, you would be very free to also put IP address and put IP version 4 address on this interface at the same time and run dual stack. You certainly can do that. On a Windows workstation, when we did that IP version 4 panel, we got the button that said obtain the address automatically or use the following address. So IP version 6 is similar. You get a button that says obtain the IP version 6 address automatically. Or if you want to manually specify address, you click this and you put in a value. So for example, on this particular environment, the default gateway host, usually the .1 host, is this value, and the workstation is 10. Now you don't have to manually specify. As a matter of fact, you probably would want to in a production environment because it's too much of a hassle to manually configure hundreds of devices. So we normally would set up DHCP or use the SLAAC function to let these devices automatically get their IP address and automatically figure out who their default gateway is. So if I want a link local address that's recognizable and easy to remember than that random garbage he comes up with, or that MAC address, he jacks the MAC address into a 64-bit address, I could go to the gigabit port and say IP address FE80::1, and then say link local. That tells me it's a link local address and not a global unique IP address, which has to start with 2 or 3. I don't want to do the static stuff. I want him to automatically do the addressing, just like we can do in IP version 4 now. We're universally not statically configuring any IP version 4 addresses, unless maybe it's a printer or a server or a router or switch. All those hundreds and thousands of workstations, gosh, let's let those automatically configure themselves. So Internet Control Message Protocol is a protocol that's going to allow these devices to figure out who their friendly neighborhood router is, and then figure out what their network prefix is. That router will tell them, and then they'll make up their own right hand part of the address. So the first method is SLAAC. The device, like an employee's desktop PC, is going to come up and he's going to send out a router solicitation, and he'll get back a router answer from the router that says, oh, this is our prefix on this network. Your default gateway value is going to be 2001 DB8 ACAD1:1. And now it's up to the workstation to come up with his own unique 64-bit value. Now he can either randomly generate a number, make it up out of nothingness. And with 64 bits, that's a lot of possible combinations. Or he can do something called EUI64, take his 48-bit MAC address and do some digital manipulation on it, turn it to a 64-bit address. And since all MAC addresses are guaranteed to be unique, that means the value he comes up with is guaranteed also to be unique. The method 2 is I can boot up and I can send my message, router solicitation the message, and he might tell me, well, here's my default gateway value, but go to this server who's going to give you the rest of the information. That's method 2. Cut me some slack. And the third method is I'm going to go to the DHCP server for all my information. So I'm sending my router solicitation message when I boot up, and he sends me back a message that says, would you mind taking your problem down the hall to the server, and he will completely help you. I'll get my network prefix, I'll get my default gateway, DNS, and all that stuff from that real actual physical server that's running. Okay, let's compare this random versus EUI process. So the workstation has generated the message, a router solicitation, and the router has told him what his prefix is. He got that from the router answering message that told him the prefix. That's got to come up with his 64 bits. So I can either randomly generate this number out of nothingness, or I can take my MAC address and massage my 48-bit MAC address into a 64-bit address that's also going to be unique in the universe. So this process, the EUI process, is we're going to take that MAC address and we're going to chop it in the middle with a fireman's axe and stick FFFE in the middle of it. And we're going to take that second hex decimal and we're going to flip it. And that comes up with a unique address. And since all 48-bit MAC addresses are guaranteed to be unique, after this division manipulation, they'll still be unique. There's no way if you do this that you can come up with two devices on the same network that have to have the exact same 64-bit identity. Now we can use a randomly generated one. Some of the versions of Windows, remember the horror that was Vista, Windows Vista? Oh my goodness. Well, at least they did. They used this randomly generated one instead of EUI64. They just simply use a random number generation. Now the problem with this is, if there's so many bits, the chances of two workstations in one network with 100 other devices coming up with the same 64-bit value is very, very small. But it could happen. So as a mechanism to check for this, after each workstation makes up his unique address by the random number generation, he's going to use DAD, duplicate address detection, and check and say, I came up with this unique value. Did anybody else happen to come up with this same exact value? He'll send it out to everybody else. If he doesn't hear any complaints back from anybody, you can't steal my address. If he doesn't hear that back, then he says, well, this must be a unique address that I can go ahead and use it. The link local address is the one they have to have it. They're going to generate one automatically. They're going to use the EUI64 process from the MAC address, or they're going to randomly generate a number and use DAD to make sure that it's unique. But you can generate, you can specify yourself. We did FE80::1, for example, in that previous example of the iOS code. If we wanted to manually specify and we use the term link local to tell them that was a link local address. But they got to have one. If you don't make up one, he's going to make up one for you. So here's an example of Windows machines that have used a couple different methods for EUI or random. Different versions of Windows use different methods. Now, Cisco routers will create a link local address. They're going to use the EUI method. They're going to take the MAC address and they're going to take that. So here's the MAC address of this particular Ethernet port 000, and he took that. Here's the 923640. It survives over here, and then they stick the FFFE in the middle, and then they flip one of the digital bits to come up with that unique value. Kind of hard to look at the number. How would you like to type that number in over and over again? I'd probably rather be FE80::1. I can type the command show interface gig 000, and it will show me. There's my link local address. There's the MAC number that I used to generate that from, and here is that manually specified address that we typed in earlier. We did IP version 6 address, and we typed in a globally unique address. And let's look at multicasting. Multicasting are only destination addresses. They're not memorized by MAC address tables. They're kind of like the broadcast address of all ones in IP version 4. But what we're going to do is we're going to group we're going to group devices together. And for example, all the OSPF routers will listen for one multicast address for routing updates. All the routers will listen to another multicast address for router solicitations from clients when they boot up. So well-known multicast addresses are the FF02::1 and 2. All nodes are in group 1, and the routers are also in group number 2. So if I want to get the attention of my friendly neighborhood router, I'm going to send the destination address of FF02::2. Oh, nearest router, please tell me what your prefix is. I need to boot up and join the network. So Ethernet NIC cards, they can filter the frame, they can look at the destination MAC address, and they can not keep so much garbage on the network. So solicited node is similar to all nodes for talking with a group. Now, how do we subnet? Oh gosh, there's so many IPv6 addresses, we shouldn't have to subnet. As a matter of fact, you guys at home with an internet service that's giving you IPv6 addressing, how many addresses do they give you? 6 trillion. Oh wow, 6 trillion addresses. That's pretty good. I don't have that many Game Boys. But IPv6 was assigned, since we have 64 bits here in the host portion, which he calls the interface ID instead of host ID, we're going to get a 64-bit prefix. If I'm big enough to be a big company that needs to subnet, I'm going to get a 48-bit prefix from the ISP. And with 16 bits, how many subnets can I create within my company or enterprise? Well, 2 to the power 16, 65,536 subnets. Now, I'm not that big, but at least I can do some subnetting. So I could take that number and say, well, this is the home office. This is branch office 1, this is branch office 2, this is branch office 3, all the way to 65,000, all those numbers that I could use. So we can increment that number, just like we did the magic number in this case is 1, 2, 3, 4, 5. Then we can allocate those networks out to my various branch offices. And don't forget, we all not only have some land-based networks, 1, 2, 3, 4 physical networks, we also have a physical network between the home office and the branch office. And that's really 5 networks we have to allocate for this. 1, 2, 3, 4, 1 and 2 and 4 and 5 for my physical offices. And subnet number 3 is the point-to-point network to connect the 2 branch offices back to each other. So in this case, we have a router with this interfaces 000 and 001, and we configured them to be subnet 1, subnet 2, and that point-to-point serial port back to the home office, that's subnet number 3. And I think that's it for this one. And now we have to go and do this one. And there's only a few slides on this one. Oh, I got to say stop sharing. Here we go. Then share files. And just a few words about ICMP, Internet Control Message Protocol. Is our protocol that allows us to mainly use ping and traceroute, our network connectivity test tools. So in IPv4, it's basic functionality. Can we reach a host? Well, I can ping the host. Can I reach him? I can't ping him. The ping timed out. Well, let me run a trace route on it and see if I figure out which one of the 10 routers the problem is occurring at. So ICMP is used by routers to sort of gossip back and forth with each other about, oh, I can't reach that network right now. That's not required. And many companies filter ICMP because if I was a bad guy, a black hat, a malicious intruder, a threat actor, and I wanted to break into your company's network, the first thing I would do is sort of scan it and see what kind of addresses you got, and figure out which ones are servers with good stuff that I can run the ransomware on. So for that case, because of that, many companies filter ping requests, ICMP, from the outside world they want to allow. So ICMP echo request, echo reply, that's our ping command. We're going to type ping to a workstation, and he's going to send a very compact echo request to that workstation. And the receiving workstation will send back a reply saying, yes, I'm here, I'm available. This doesn't take much processing power on either machine to take place, and they're very small packets. They don't waste a lot of network bandwidth. If the host machine was not available, in this case, If there was a, phone line was down or something, oops, that's back on here. If this phone line went down, then he wouldn't be able to receive a reply back. So we can have some messages like the destination is not reachable, port is unreachable, host is unreachable. IP version 6 adds a little bit of additional functionality to ICMP. They use it for, so a host workstation, when he boots up, he can do the router solicitation and learn who his home router is and so forth. So similar, but slightly different. The kind of sense that Portuguese is similar to Spanish, but slightly different. For IP version 4, when we ping, we send a time to live field in the packet. And IP version 6, this is called time exceeded instead of time to live. But this is what traceroute uses. If I send traceroute and I want to figure out, is this error between router 5 and 6 of those 10 routers, or where is it at? Traceroute will tell me where the connection failed. Ping only tells me whether it succeeds or fails as a whole, but traceroute will get me more granular. I can figure out what's between router 5 and 6, and those are our routers, and we got to fix them. Or is routers 5 and 6 belong to our ISP? I can't touch those, but I can call the ISP and complain about the issue. So in IP version 6, we've got this neighbor discovery protocol, neighbor ND or NDP. The routers will respond to router solicitation messages, and they'll send back a router advertisement or a router answer with the information about, well, for example, what's the network prefix we're on? I need to know my network prefix. I can randomly generate my own identity with the interface ID or the host ID, but I need to know what my network prefix is. And I need to determine where my neighbors are. So if, for example, neighbor solicitation and neighbor advertisement, this is the replacement for ARP. If I want to send something to a neighbor, well, I've got to encapsulate that in an Ethernet frame, and I need to know his Ethernet destination address. So I send out a neighbor solicitation message. If your IP address is 2001 DB8 ACAD : 10, please send me back your MAC address so I can put my message I wish to send to you in this Ethernet frame, and now I know your destination MAC address. So it's the same problem we have to IP version 4. I know my own IP address. I know my own MAC address. I know your IP address, but I don't know your physical MAC address. And I need to ask you to tell it to me. So router advertisement messages are sent by routers every 200 seconds. So any device can hear it and figure out what network he's on. And then a host, that's SLAAC, what I call cut me some slack. Now he knows what his first 64 bits, the first half of his address is. And he'll set his default gateway to the link local address of that router, which is typically FE80::1. Ooh. There we go, pencil back on. An IP version 6 router will also send out back a router advertisement message in response to a router solicitation message, say from a PC workstation that just boots up. So R1 is going to send, PC1 sends a router solicitation message. He just woke up, he's static, he's not statically configured. He says, get the address automatically. He doesn't know what address he should use that. He's a brand new machine, just got built. So he sends the router solicitation message. The router R1 replies and says, well, I'm your friendly neighborhood router. This is my IP address. And you're going to use this prefix on the network. And just use SLAAC and make up something yourself. We had 3 ways. We had SLAAC, half SLAAC, and go to the DHCP server. DAD, duplicate address detection, it's not required, but if you're using not the EUI64 method, but just a randomly generated method, it's insurance that 2 devices don't happen to make up the exact same randomly generated number. Very low probability of this occurring because there's billions and billions and trillions of possible 64-bit addresses. So if I need to determine your MAC address, I know my IP address, I know my MAC address, I know your IP address, I don't know your MAC address. I'm gonna send a neighbor solicitation message to you and say, please send me back your MAC address. It's exactly the same function as when you send out an ARP request in IP version 4 and the workstation that says, oh, this is my IP address, and he tells you what his MAC address is. So you can put something now in an Ethernet frame, you have his MAC address, and you can create that destination part of the MAC address when you create that Ethernet frame. Okay, ping and traceroute are our 2 big troubleshooting tools. Ping is echo request and echo reply. That's end-to-end connectivity. Notice in the chart here, the first one failed. The period is timeout, and the exclamation points are good, 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 good. The first one, usually there's 1 or 2 dots because the ARP process is taking place. Even in IP version 6, you may get a dot or two because he's not using ARP request and ARP reply. He's using the neighbor solicitation method instead, but he's learning that MAC address, and the first 1 or 2 pings may fail, and then it'll keep working for a while. So it's common for the first ping or so to timeout. Now let's do some testing here. First of all, we're going to ping our very own loopback port, 127.0.0.1, or ::1 for IP version 6. See, in IP version 4, we wasted an entire Class A network just for the 127.0.0.1. In IP version 6, we don't waste but 1 address for it. So it's much more, it doesn't waste so many addresses. If I don't get a message back for this, it means that TCP/IP probably wasn't checkmarked in the box. So I'm going to ping my default gateway value, 10.0.0.254 in this particular case. That proves I can communicate all the way to the default gateway. He was able to hear my request and he gave me a reply. I have proved network connectivity from PC through the switch to the friendly neighborhood router. Then I'm going to ping, a server back at the home office, something like that, to go through the lease line and test everything. So if the ping is good, that means the entire network is good between those 2 selected arbitrary points that you did the ping test on. However, some network administrators do some filtering on ping. There may be a security restriction, and you may not be able to use it on your network. The most common thing I've seen is it's allowed within the internal company network, but not allowed from other people in the outside world to come in and scan the network of the company to look for vulnerabilities and problems. Now, ping only works as a succeeds or fails as a whole. Doesn't tell me if the problem occurs. Where is the problem exactly? And this is where traceroute is used. Traceroute is ping's it's like ping on steroids is what I call it. It allows you to check if there's 10 routers between you and the host and the destination host. It'll essentially ping the first router, the second router, the third router, the fourth router using some time to live trickery. And that way, if there's a failure between router 4 and router 5, for example, you'll get all the way to router 4, and then you won't be able to get to router 5 or 6 or 7 or 8. You'll know the problem is between router 4 and router 5. Well, you really divided the problem now till you know it's between one particular component, and you don't know, well, what could be 10 different routers or different networks. Which one is it? Ping didn't tell you that answer. Traceroute told you that answer. Now you can narrow down the problem, narrow the scope of the problem. So this is the way this time to live magic works. I'm going to send out, when I tap the traceroute command, the traceroute program is going to send out a packet with the time to live set to 1. When it encounters the very first router, that router will subtract 1 from that value. It's going to decrement that 1 to 0, and when the router receives a packet and the time to live has decremented to 0, that's as a loop prevention mechanism, he will not further process the route. He'll drop the packet. He will send a message back to the original host machine saying time to live exceeded. Now I know the IP address of the first router. Then I'll send out another packet with the time to live to 2. It'll go through the first router, 2 minus 1 is 1. The packet survives, is sent to the router number 2. Router number 2 now receives it as 1, subtracted to 0. Router 2 says, oh, I got to drop you, sorry, buddy. And he sends back as a courtesy to the original host machine, time to live exceeded from router 2, and now I know router 2 is. And this is repeated to the network till all 10 routers or how many routers there are. I've learned the hop-by-hop pathway of the packet, my packet is taken to the network. And that way I can tell exactly where the problem is. So if it's at my internet service provider, I can call it. If it's my stuff, well, it's my stuff, I get to fix it. Okay, so I've covered IP version 4 legacy addressing and subnetting. We've covered IP version 6, the updates to IP version 6, and we've taken a little look here at ICMP. And so in our lab on Wednesday, we're going to do a lab where we actually have a full switch and router network, and you'll configure some IP addresses on the router and switch and the PC, and everybody will be able to pitch switch, router, PC will all be able to ping each other. Okay, I'm going to hold on. I'm going to stop this recording function. We'll stop the tape.